Welcome to ECE 302. This is lecture 3.6 on binomial random variables. I am Professor Stanley Chan. Today we're going to look at the second type of discrete random variables, which is the binomial random variable. The binomial random variable has a very strong linkage with the Bernoulli random variable, which we studied last time. Now, to motivate the discussion of the binomial random variables, I want to tell you a little story about an image sensor. I hope to use this example to motivate the discussion and to show you some practical application of this binomial random variable. This is a type of image sensor which our lab has been working on for a few years. The idea was originally proposed back in 2005 by Eric Fossum from Dartmouth College. This sensor is called the quantum image sensor. It is a very special sensor in the sense that it does not acquire image as it is. Instead, it acquires images using binary bits. So here we want to look at how this image sensor works. And then during this discussion, you will find out that there are some very interesting statistics about the sensor. And then we want to discuss the statistics of the sensor through the binomial random variables. So let's look at how the sensor works. This sensor, since it is a binary image sensor, all the pixels that it acquires will be binary, meaning that it could be either 0 or 1. So here, if you look at this image plane, first of all, you will have multiple frames. And here I'm showing you 3 frames. In each frame, you will have many pixels. If I zoom into a small region here, then I will see that you have a lot of binary bits. If I zoom in further, you can see that it is either +1 or 0. So each pixel is binary, is either 1 or 0. Now, how do you determine whether the pixel is 1 or 0? That really comes to the nature of the photons. So imagine that you have a pixel, and then the photon is like a raindrop. Okay, and so as the photon comes to your pixel, it depends on how fast that photon comes. And in other words, it also depends on how strong the scene is. So imagine that you have an image which you have a very bright scene, and then you have some really dark region. Pixels in this area, you will have a lot of ones. So if you zoom in, you will have a lot of ones. Pixels here is very dark, and so you will have most of them being zeros. The photon arrival process is a random process. It follows a process called the Poisson process, which we haven't talked about yet. But all you need to know is that this random process, as it is called, it is random. And therefore, even though it is a very bright scene, you're not guaranteed to get just one, and occasionally you may get some zeros. Now, this zero could come from the fact that sometimes the photon may not come to your pixel, or sometimes your circuit has any kind of readout noise. And so the density of the ones and zeros is determined by the brightness of the scene. Like in this image, you look at the Liberty statue, and then here you can see that there are lots of brighter pixels, and here you have darker pixels. The brighter pixels, you will have more ones, and then the darker pixels should have more zeros. Now, you're not guaranteed to get only the zeros or only the ones, because even in those bright regions, you will still have some zeros. So the probability of getting a 1 is determined by this number p. Now, certainly this p is, of course, a location dependent. So the p here in this region could be a very large p, and then the p here, you will have a very small p. So this is how the sensor works. You put the sensor out there. Depending on how bright the scene is, the sensor is going to generate binary bitmaps. The density of the binary bitmap depends on the brightness of the scene. The brighter the region, the more ones that you will get. However, the presence or absence of the ones and zeros, they're still random. So even if you have a very bright scene, you can still have 1 and 0. Same for the dark scenes. Okay, so this is the sensor. Now you may wonder, 2 questions. 1, how the sensor can ever be useful to capture better images. And 2, how is this ever related to the binomial random variable, which is the subject of this lecture. So let me quickly talk about the application of the sensor to make sure that you really appreciate this new technology. Here is a very latest work that our group has been publishing in the European Conference on Computer Vision. Here we are comparing this new type of image sensor, the QIS, versus the conventional CMOS image sensor, or CIS in short. We are using this new sensor to perform very, very low light image classification. So this is an image captured at 0.5 photons per pixel. Now 0.25 photons per pixel is extremely dark environment. This is the image that the raw sensor sees. And here is the image that the raw CMOS sensor sees. Now, we are going to send this pattern, extremely dark pattern, into a classifier. And of course, the classifier has to be well trained using new machine learning technologies. But if you send this image to a new classifier, then you can see that the classifier will return you a label. And in this case, it does return you the label black bear. And in this case, it's returning you the correct label as well. Versus the CMOS image sensor, although it does give you some labels, but they are wrong. Why? It's because, 1, that the CMOS image sensor has a lot worse performance at low light compared to the quantum image sensor, because you are counting every photon, and then this binary sensing mechanism will help you capture as much photon as you can, and therefore you will be able to reconstruct a better image. Compared to the CMOS image sensors, the CMOS image sensors has full of noise, and so there isn't any signal there, and so the classification will not be good even if you use the best image classifiers. The small inset here, they show the image that you will normally get by sending this image to an image denoising algorithm. And you can see that using the new sensor, this binary sensor, you will be able to see some pattern. Although it is not that obvious, this little pattern is sufficient for the image classifier to work. And so the implication is that with the sensor, you can actually see a lot better in low light environments. What else can you do? You can do image reconstruction using the sensor. You can reconstruct a moving fan sequence where the fan is rotating at a high speed, and then you can still recover the moving fan. You can have a very, very noisy image captured at very, very low light situation, and then you can design new algorithms to reconstruct the image. So with this sensor, you can do a lot better jobs in low light imaging, and which this has a lot of applications in military, surveillance, or even biomedical imaging. Now, let us ask the second question. Why is the sensor ever related to the binomial random variable, which is the subject of this lecture? Recall that the binary bits that the sensor sees will be 1 and 0. So suppose this is your pixel, and then you're observing 1, 0, 1, 0, and so on. This is the binary bit stream that you are seeing over the time. Then over a certain period of time, you ask, what is the average number of ones that I will be able to see? Then what you need to do is to sum all the number of bits. Sometimes you get 1, sometimes you get 0. You sum them up. Then you will be able to get another random variable. So let me define this random variable as x. And then x will be the summation of I going from 1 to n. And let's call this I1, I2, and so on. Okay? And so now you're summing over all the ij's. Then we know that this ij, this is a Bernoulli random variable with certain probability p. Now, let me remind you, the p really depends on the location. The p here will be different from the p there. Okay, so this would be a large p because it's a very bright region. This would be a very small p because it's a very dark region. But anyway, we're looking at this x, and x, of course, the x here would be different from the x there. Okay, so now we are looking at random variable x. It is a sum of the Bernoulli random variables of p, and I'm looking at one particular location. Now you're summing all these Bernoulli random variables, and we ask, what is the statistics of this random variable x? And it turns out that this random variable x is a binomial random variable. Okay, so what we want to do in this lecture is to understand more about this binomial random variable, with the hope that we can understand the relationship between this binomial and Bernoulli, and how do we calculate the expectation, the moments, the variance, the CDFs, and all kinds of statistical properties that we need to know about the binomial random variable. So here is the outline of today's lecture. We want to first define the binomial random variables, and then we want to talk about the relationship with Bernoulli, variance, and expectation, and then we'll come back to the application using this binary image sensor again. So to start with, let us talk about the definition of a binomial random variable. The binomial random variable, since it is a random variable, we should expect that it will have a probability mass function, just like the Bernoulli random variable. Now, in the Bernoulli random variable, we have two states. But for the binomial random variable, we will have a total of n states. The probability mass for this binomial random variable is given by this equation. And let me remind you, this n choose k is the n factorial divided by k factorial and n minus k factorial. This k goes with p, and then this n minus k goes with 1 minus p. We will discuss the meaning of this expression shortly. But for the moment, let us also try to understand one notation. We will write the random variable x using this notation to denote that it comes from a binomial random variable. Note that in the binomial random variable, we have two parameters, n and p. N denotes the number of Bernoulli trials. Okay, so imagine that you have a pixel here, and then you have ones and zeros, and we ask over a period of time, and altogether there are n measurements, and what is the sum? Okay, so here is the sum. So what is the sum here? And then the sum would count at most to n. So this is the first parameter. The second parameter is p. P is the probability of getting a 1 from this Bernoulli random variable. So you can think as the problem of knowing the number of heads in a coin flipping n times. Okay, so this is the binomial random variable. It has two parameters. As long as I tell you the two parameters, you will be able to specify this binomial random variable. This is somewhat different from the Bernoulli case, which is quantified by only one parameter, p. In binomial, you're quantifying by two parameters, n and p. This is also similar to the normal random variable, which is something that we will discuss later on. A normal random variable or the Gaussian random variable is characterized by the mean and also the standard deviation. Okay, so in the binomial random variable, it's characterized by n and p, two parameters. Okay, let us talk about the formula. The magical formula of n choose k and then p to the power k and 1 minus p to the power n minus k. Let us consider the following example where you try to flip the coin 3 times. Okay, so we're defining a random variable x, which is defined as I1 plus I2 plus I3, where each I is a Bernoulli random variable. So this I is Bernoulli with probability p. And so the total number of coin flips is 3. And we ask, what is the probability of getting 3 heads? Okay, so essentially we're asking, what is the probability mass of this random variable x when it is evaluated at 3? So px at 3 is really the probability of getting 3 heads. And since all these coin flips, they're independent events, you can write this intersection of 3 heads into the products of the 3 probabilities. Each one will be p, and so you will have p to the power 3. So that's easy. Now, let us try to map this p to the power 3 into our equation. So here we have px of 3. This is the same as the probability that x equals to 3. The number of heads equals to 3. And according to our definition, this is 3 choose 3 p to the power 3, and then 1 minus p to the power 3 minus 3. And so this will give you 1 times p to the power 3, and then 1 minus p to the power 0. And so you carry out the calculation, this will give you p to the power 3. You can see that this n choose k is actually playing a role in terms of telling you what is the coefficient going with this p to the power 3. Now, if you don't believe me, we can also calculate one more case to make sure that this quantity here, n choose k, should be present. Let us consider the case where x equals to 2. When x equals to 2, what do you want? X is the number of heads. And so if you have 2 heads, then you really need to have head and tail, or head, tail, head, or tail, head, head. So these 3, they are computed as a union because any one of these cases can give you a head, and then you have 3 different possibilities. So now these 3, they are disjoint events, And so you can write them as the sum of the three different events. And then you look at all these head and tails. Since they are independent, you just need to count how many heads and how many tails that you have. And in this case, you have two heads, so you have p to the power 2, and then one tail, so you have 1 minus p. Same for here. You have two heads, so you have p squared, and then one tail, you have 1 minus p. Also for this one. And since you have three of those cases, you have a 3 here. Now, let us go back to the calculation. Suppose we want to look at px evaluated at 2. This is the probability that x equals to 2. And so let's plug in the formula. This is 3 choose 2, p to the power 2, and 1 minus p to the power 3 minus 2. So you do this calculation, you will have this 3 times p squared times 1 minus p. And you can see that this matches exactly with this formula. So, in general, if you have a binomial random variable with a parameter n as the number of Bernoulli trials, then this px of k can be written as the following form. How do we understand this form? This quantity really specifies the number of combinations that you can have. So imagine that you have a head and tail, and you want to get one head and two tails. So that means you can have different combinations. You can have this, and then you can have this. See that? Okay, so these number of combinations is essentially asking you that I have 3 color balls, okay, and then 2 of those will have the same color. And what is the combination? What is the number of combinations? That will give you n choose k. How about this? This quantity says that I do want to get how many oranges. Okay, and in this case, k could be equals to 1, and so you get 1 orange. And then the other one, if it is not orange, then it has to be blue. Okay, because the underlying random variable is a Bernoulli, so you have either one case or the other. So that will give you this 1 minus p, and then the probability of getting the other one should be n minus k, because k has gone to the other case. And so you're counting this probability. This is the product of all the individual events, and then you choose n. You have this n choose k to take care of the redundant possibilities. That will give you the probability mass. The shape of a binomial probability mass function is as follows. As I said, since you have 2 parameters, you really need to plot 2 different sets of curves. The first set of curves is that we assume that you have a fixed number of n's, and then we played around this. We played around with this probability p. Okay, and this should be 0.9. And this should be 0.5. Okay, so when you try to plot this out, you will be able to see that when p equals to a small number, then most of the samples will be concentrated in the lower end. If p is a big number, then all the mass will be concentrated at the high end. And if p is 0.5, then it will be centered somewhere in the middle. So this is the shape of the binomial PMF. It changes according to the underlying probability p. Okay, it shifts all the way from the left to the right. Now, on the other hand, if I fix the probability p equals to 0.5, and I change the number of n's, then you can see that for small n, I'm concentrated here, and for larger n's, I'm going towards the other side. It is also interesting to observe that as you make the n bigger and bigger, the distribution becomes more and more like a bell shape. And that's why the binomial at the limit, it can be approximated by a Gaussian random variable. We can calculate the moments of the binomial random variable. The moments are given by the following formulas. The expectation of x is n times p. The expectation of x squared is n times np times np plus 1 minus p. The variance is np times 1 minus p. Now, to calculate all these expectations, moments, and variance, we can just follow the first principle. And here is one example. In order to calculate the expectation of x, what you need to do is to plug in the PMF. This is px of k. And then here you have a k. Then you sum everything up. That will give you the expectation. So when you try to calculate this, then you notice that we need to carry out the multiplication and also the summation with respect to this k. And so you see that there's a k here, there's a k factorial here, and so they need to cancel out, and then you have k minus 1 factorial. And then the calculation has to carry on, and I say that there will be a few more steps, and then eventually you will get to this point. Now, how do we do that? We are going to use the binomial identity and also the infinite series properties of a binomial series to calculate this expectation of x. How about the second moment and variance? They will follow the exact same principle. Now, what I want to do is not to go over the details of those derivations because those would be straightforward. It's just a little bit tedious. I want to show you an alternative proof to get the expectation and also the variance. The alternative proof is based on the fact that x is the sum of individual Bernoulli random variables. And so you will have x equals to I1 plus I2 plus etc. all the way to In. Now we want to ask, what is the expectation of x? And to answer this question, we also know that the expectation of ij is p, okay? Because ij is a Bernoulli random variable with a parameter p. How about the variance? The variance of ij is p times 1 minus p. So let's calculate this expectation. The expectation of x is the expectation of I1 plus all the way to In. And then this is the expectation of I1 plus plus the expectation of In. Now, how can I break this expectation into individual expectations? This is something called the independence across multiple random variables. This is something that we will discuss later on, okay, in when we go to chapter 5. But if we accept this fact, then we know that the expectations can be calculated by summing the independent expectations. And since each of them is just p, then we know that how many p's are there? It will be n times p. And so we have shown that the expectation of x is n times p. Similarly, we can calculate the variance of x. The variance of x is the variance of I1 plus I2 plus plus In. And again, by this a trait called the independence of multiple random variables, something that we will discuss later on in our course, you can show that it will become the variance of I1 plus the variance of I2 plus plus the variance of In, and then that will give you p times 1 minus p plus p times 1 minus p plus plus p times 1 minus p. When you sum everything up, you will have n times the p and 1 minus p. What is this p times 1 minus p? This is the variance of the individual Bernoulli random variable. And you have n of those. So you can check the formulas when you have expectation of x. This is n times p, and should be quite intuitive because you flip the Bernoulli coin n times. The variance is just n times the variance of the individual Bernoulli random variables. The CDF, or the cumulative distribution function of a binomial random variable, is given by this formula. There shouldn't be any surprise because fx of k is defined as the probability that k is less than or equals to k. And so what you need to do is to really the sum your index L from 0 all the way to k, and here it will be your probability mass function. Unfortunately, at this point, there's no simple algebra that can help you simplify this expression. So what I do is that I will just plot out numerically what is the PMF and the corresponding CDF. And you can see that the CDF really is a staircase function that the height of all these jumps will correspond to the height of these impulses. Now, let us come back to the binary sensor, which I introduced in the beginning. We want to ask, how do we model the random variable x, which is equal to the number of ones observed in 100 measurements, okay, or in general, n measurements? Now, we know that this x is the summation of ij, and j equals to 1 to n. Each ij is a Bernoulli random variable. And so we also know that the expectation of x, it will become n times the probability p, where this ij is a Bernoulli with a parameter p. Furthermore, we know that the variance of this x is n times p times 1 minus p. Okay, so now given this sensor, here we have some binary pixels. So sometimes it is 0, sometimes it is 1, and so on. Okay, so here you have some zeros and ones, and then you measure this multiple times. If you trace along this time axis, then you will get a bunch of ones and zeros, and then these, they will have a mean of n times p. So we know that p comes from the intensity of the pixel, and so by calculating this average, you will be able to tell what is the expected intensity in that region. So that will lead to a very interesting inverse problem, and by solving that inverse problem, you will be able to recover a scene. So I hope that with this lecture here, you have seen some non-trivial applications of the binomial random variable. Hopefully something that you have never seen before. Hopefully this something can motivate you to study more about the binomial random variables. It is not just flipping a coin n times and counting the number of heads. It is actually used in practical engineering problems. With that, I will thank you for watching, and I encourage you to work on our homework problems. And if you have any question, please feel free to ask. Thank you.